Okay, so my name is Brandon. My project is called Zynth. Um, yeah, I just took the word synth and put a Z in front of it. I know, lame, but that's what I came up with, and it kind of just stuck. So, all right, I'll just give you a quick introduction about me. This is going to be supposed to be a short presentation, so I can't really spend too much time. But I've been programming for 13 years. I've been a pianist for 20 years, and I also, even though I don't really play sax and violin these days, I have in the past for 9 and 6 years respectively. My other main hobby is rock climbing, so that's a little bit about me. Okay, so Zynth is an additive MIDI synthesizer. So if you're not familiar with MIDI, it is a protocol to send musical events to like a computer device or in between other MIDI controllers and stuff. And basically, it boils down to did you turn a note on, off, and then at what velocity did you do that? So like if you hit a note softly versus with more force, that is in the protocol. It's actually a very simple protocol, but that's the gist of it. And then the synthesizer takes those inputs and will generate a complex audio output in real time. And that's kind of that's like the main hurdle here is the real time aspect. And we're looking for in the ballpark of 5 milliseconds. For me, anything above 10 milliseconds, kind of unusable. Like if you're trying to play a fast passage, it'll kind of, your brain will trip over the notes because there's that little bit of delay. You'd be surprised how sensitive your ears are to like any kind of latency like that. It's much worse than any kind of visual latency. It's kind of weird actually. Theoretically, you want to go down to like 1 millisecond if you could, but 5 is like pretty good. So I'm shooting for that as like a goal. So basically, the most basic sound wave you can have is a sine wave, which basically is a sound wave that consists of one frequency and one frequency only. And it would sound kind of like this. Well, if I turn the vibrato off. But... No, I can't turn the vibrato off apparently. Okay, never mind. So it sounds kind of bland. That's the most basic thing. And then if you want to get more complex sounds, what you do is you add harmonics. So basically, the harmonics are the integer multiples of the fundamental frequency. So if I'm playing a note, say A for 440 hertz, the harmonics would be double, so 880 hertz, triple, I'm not going to do the math on that, but you can do it yourself, quadruple, quintuple, and so on. So like basically integer multiples. And all like musical sounds, so like sounds that have a sort of defined frequency are made up of these harmonics. And that's how you get different timbres. So the reason you can tell one sound from another, like one instrument sounds very clearly different from another instrument, even if they're playing the same exact note, is because of the timbre. And the timbre is basically the ratios or like how much each harmonic contributes to the overall sound. Okay, I'm really realizing this presentation is gonna probably take a while, but hopefully I can get through this kind of quickly. Just a quick demonstration. So if we treat our harmonics as a bunch of sine waves, I did the sine of nx basically means the nth harmonic will be n times the frequency. So you think of it as the sine of the n is like the frequency basically. So the number harmonic. And then f of n, think of that as how much that harmonic contributes to the overall waveform. So right now I have capital N equals 1, which means I'm only adding up one frequency. This is your pure tone sine wave. And then if I add in more harmonics, you can see how it changes the waveform. The waveform is more complex. It has more wiggles between the two, like within one period. It has a bunch more wiggles. But overall, it's still the same frequency, right? It's still, the period of the wave is still from 0 to 2 pi, even though it does these crazy wiggles in between. And because we're only using the harmonics, it's always going to still be that same frequency. And so I'm actually doing a sum here that in the limit to infinity would go to a sawtooth wave, basically. So a sawtooth is if the contribution of each harmonic is inversely proportional to that harmonic, so 1 over n, basically. And then if I change, so instead of doing 1 over n, say I did like n squared, so if I change a to 2, So now the contribution of each harmonic is 1 over n squared instead of 1 over n. So it favors the lower harmonics rather than the higher harmonics. You get this kind of interesting wave shape. And you can see what happens if we start with just one harmonic. It's still just the sine wave. And then as we add more harmonics, we get closer and closer to the limiting shape, which is something like that. And if we can slide this exponent value here and get more sawtooth wave versus more sine wave. And this will be a more harmonically rich sound, a more like, it'll be kind of a more nasally sound and a more, I don't know how to explain it. I could just demonstrate it, I guess. So this is more of a pure tone. And then as I add more harmonics, or as I decrease the exponent and make it more of a sawtooth wave, it's like that. Right? So that's essentially timbre, because it's the same note. You can clearly, it's the same pitch, right? You sing it, right? It's the same note, but it's clearly different. It's like versus eh. It's a different timbre. And so that's how we're doing that. Okay, so that was probably way too long of an explanation. I'll try to speed up this up. Okay, so that's in an ideal world. In reality, instruments also produce some inharmonic frequencies, which also contribute to the sound, which is something I am also experimenting with including in my synthesizer, but we will kind of like forget about that for now. One interesting is how many harmonics would we realistically need to like sort of replicate any sound we would want. So we can actually do a calculation here. The MIDI protocol specifies 128 possible notes, which basically covers the entire, more than the entire usable audible range that you would ever want. Because if you think about a piano, it's only 88 keys. So this goes about 2 octaves below and 2 octaves above the piano. So more than you would ever need. I am using a 48 kilohertz sample rate, which means I'm outputting 48,000 samples per second. And then there's this thing called the Nyquist frequency, which basically says that you only really need to include frequencies up to half the sampling rate, so 24,000 hertz. Because beyond that, your sampling rate is just not fast enough for that to even like make a difference. You can probably Google that later for a better explanation. But so what that means is that if we take the lowest note, or like for each MIDI note, if we take that frequency, 24,000 divided by that frequency, you would get the number of harmonics you would need to basically cover the entire audible range. And if you add that up for all 128 possible MIDI notes, you get that you would need about 52,205 harmonics. So keep that number in mind. That's kind of like a good goal to have, to be like, okay, I can basically replicate any sound if I have this many harmonics going in real time. Okay, so the interesting dilemma with a synthesizer is that we have a real-time requirement here. You know, I can't just wait an hour to render my audio. I need it now, and I need it like in 5 milliseconds, right? So that's a huge ask. So at 48 kilohertz, that would be a 240 sample buffer. I have to fill that every 5 milliseconds. And it's even more than that, because it's not just that I have to fill 240 samples every 5 milliseconds in total, like over the course of my song or something like that. It's every 5 milliseconds I need to hit that deadline, right? And so if there's some weird pause in the processing for a couple milliseconds, you might miss your deadline and you'll get a pop in the audio, and your ears are very sensitive to that. It's not good. You do not want that. Especially if you're like performing something, you do not want any pops in the audio. So what are our sources of latency? Could be a lot of things, but the main ones would be like syscalls, because doing the context switch to the operating system and back again it doesn't take that long, like in the context of most programs, but when we're talking a real-time scenario, that kind of thing takes a long time. Memory allocation can be a source of latency if it's doing a syscall, right? And so if you're just calling malloc, right, that has a chance that it will request a page from the operating system, and that's a syscall, and that can be a source of latency. Acquiring a mutex, you're basically like, your program is basically like halting, just waiting for something else to be ready. So that's a source of latency. And if you're calling any libraries that do those things, right? So all of your dependencies that you're using in your hot loop, you need to make sure that it's not doing any of this stuff. And finally, even if you do everything right and your program is perfect, the OS might just decide not to schedule your thread. So that's another problem. So basically, yeah, you want to have a tight control over all the code running in your hot loop. And that makes Zig probably the most suited language in existence for that use case, because we have explicit allocations, we have no hidden control flow, all that good stuff, right? So, I mean, and also keep in mind that Andrew Kelly created Zig when he was trying to make a digital audio workstation, right, in C++. So it's no surprise that like audio applications are kind of well suited to Zig. So that's kind of cool. All right. Sorry, how am I doing on time? Do I need to like speed this up?
Don't worry about it.
Okay. Sorry. Yeah. So basically, the core engine of the synthesizer basically boils down to calculating the sine of the phase of the harmonic or the partial that we're calculating, multiplied by its amplitude, which is basically the contribution of that harmonic in the total sum that I was showing you before. And we're going to add a bunch of these together. So single threaded, I didn't really like benchmark it recently, but I mean, I don't know exactly, but it's in the ballpark of like 500, 600 partials that I can calculate in real time on like this laptop or that laptop. So I could probably do even more, but and so that means we're doing 500 times 48,000 of these calculations right here every second. Okay. Now, my desktop PC at home is a 6-core 12-thread Ryzen CPU with AVX2 support. So that is the SIMD instruction set. In theory, in a perfect world, if you could literally just multiply your performance like this, you would get 12 times 12 for each of the threads times 8, because you can do 8 float 32s in one AVX2 register. So theoretically, I would get 96 times the performance, which would give us 50,000 harmonics. That's what we were trying to, that was our goal, which is pretty cool, right? All right, so let's see. Okay. So the first way that we're going to try to achieve this is with SIMD, like I was saying. And it's probably one of the easiest ways to add parallelism to your code, especially when you're doing math operations on large data sets, because you don't have to worry about spawning threads, synchronizing them. It makes your code relatively easy to reason about and understand compared to multi-threading your code. So if you're trying to get a performance boost and you're doing a lot of just cranking out math operations, you might want to look into SIMD. So basically there's special CPU instructions that work with larger register sizes. For example, AVX2 is 256-bit. There's also AVX 512 now, which is 512-bit. But I don't have a CPU with that, so yeah, that's coming. That's new. And Zig makes it super easy to tap into this power that your CPU has with the @vector types, right? And so the idea is that if you have your data in a huge array, which in my case I do, I basically have a bunch of arrays of like 3,000 harmonics each in a single array. And what you basically want to do is just extract a chunk from that array, the size of your SIMD register, do your operation on it, and then store it back. And then you instantly get like 8x the performance. So what are some of the pitfalls? So the first time, if you're just like reading through the Zig language reference and you see these @vector types, you might think, oh, I could just have 1,000 float 32s in a vector, right? Well, not quite. So you probably don't want to do that. You probably don't want to be storing the vector types directly in your data structure. You probably want to be storing your data in an array, and you're only using the @vector types temporarily to do the math operations on the numbers and then store them back in the array. So that's one thing to keep in mind. The other thing, like I said, you don't want to use an extremely large length, because the alignment of the @vector type is dependent on how many items you have in the vector. So you just have 1,000 float 32s, your alignment is going to be like massive. So yeah, don't do that. Right, so remember that it actually has to use your CPU instructions at the end of the day. It's not just some magical thing. Yeah.
Is there like a U size equivalent, like based on what SIMD instructions, the width?
Yeah, so what you'd want to use for that, did I put it here? I think no, I didn't put it here. If you use standard.cindy.suggest vector length, you'll basically get the size that you're going to want to use. So like on both my laptop here and my desktop at home, it gives me 8. If I say suggest vector size for F32, it gives me 8. And that's basically because I have AVX2, and that gives me 8 float 32s.
And are there compiler flags that you have to enable?
No.
To just
yeah, not in Zig. I don't know if you would have to in C. I don't know, but in Zig, no, it's easy.
In general, in C you have to. Yeah. And another quick question: what the math you're doing is very reminiscent of a Fourier transform.
Yes.
Fast Fourier has all sorts of clever, basically makes the ON O log N. Have you looked into that?
I'm sure there are algorithms and shortcuts that could be taken here. I'm not at that stage yet. I'm literally learning this stuff as I go, pretty much. I've never done anything with audio before. This is like just a hobby project that I'm just trying out.
In no signal processing, basically the fact that sine, there's a relationship between sine of 2x and sine of x.
Yeah.
And 4x and blah, 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 right? And Fast Fourier leverages these relationships so that you can cut down on the number.
It's definitely something I want to look into. The only potential problem I see is that whatever the algorithm this is, whatever shortcuts these are, they have to be able to be done quickly. So depending on the math involved, I don't know. If it can't be done super quick, it might not be viable, but it would definitely be something to look into.
It's called Fast Fourier because it's fast, not because it's complicated.
Yes, but I don't know if it's.
It might introduce latency. Like it might be on the milliseconds level, but it might Fourier transform is a non-real time thing, by definition, because you're working on the frequency domain.
Yeah.
Not the time domain.
Yeah, no, it's a totally good point. It's actually something I've considered looking. It's like in my notes list somewhere. Like look into this. But yeah, I just haven't gotten around to it yet, and I don't know the viability. It might not.
Yeah.
So yeah, that's. But you're correct in that. Essentially, what I'm doing is building up the Fourier or the Fourier series, right, from scratch.
Yeah.
So.
Just quickly, I'm pretty sure we have to do this for a specific kind of CPU. That's
yeah, because I think by default just use like native.
Generic CPU, which means
So if you were to use generic, you're probably not going to get AVX2. You're probably going to get some baseline.
Yeah.
That's a good point. But if you're just Zig building on the local machine, it'll do the native stuff for you automatically. So you don't have to worry about that.
For runtime detection.
What do you mean?
So like if you can, presumably if you have AVX2 and you compile on that machine, you detect, okay, this machine has AVX2.
So the problem is that all the at vector types, the length is comp time. So what you would have to, if you wanted to do that, you would have to like generate the code, like use some generics or something to generate the code for every vector type length that you want to support, and basically have that code duplication there. As far as I can understand, that would be the only way to do that.
I haven't heard it.
But the content thing, if you ask at runtime, does this do the thing? It'll tell you yes or no.
Yeah.
Yeah.
I think you don't. That's not. So.
If you do optimization where you generate different versions for every initial unroll, although unroll the initial parameters.
Yeah, so it would blow your binary, but you could do something like that. Yeah. Okay, so I just want to do a quick little sort of a game because it's kind of interesting. Like one of the pitfalls of Cindy is that you need to know that the code you're generating is actually generating vectorized code. So if we just have a function that takes in 2 vectors and returns a vector, right? So v1 plus v2, the output is very clearly using your vector instructions. It's just one instruction. How nice, right? I added 8 floats in one instruction. Pretty cool. And the same would be if I did times. It would be one instruction, vmul. Okay, so now I'm going to comment it out so you don't see the answer yet. Oh, I need to also comment this in because I'm not going to use v2 now. Yay, Zig. For that unused variables. Okay, so if I do, for example, the exponential of v1. Now the Zig language reference says the @x function, or not function, but built in, right? Because it might not be a function, supports vectors. And it will say it will use a hardware instruction if available. And so if you see that in language reference, you might think, oh, it's totally cool then to just put an @x in my vectorized code, right? It'll be great. Well, let's see. I'm not really hiding the answer too much in the way I'm talking, so I'll just give this one away. You get this.
Oh my god.
So you probably made your code slower even maybe by doing this. I don't know. I'm not going to benchmark it, but it's not great. It's going to be on par with like the unvectorized version. You can see it's literally calling this xf at plt 8 times for all of your floats.
Is this because the compiler isn't smart enough, or what's the reason?
So you could theoretically write a version of exp that does the vectorization, but either the standard library hasn't done that work, or like, well, first of all, if there's no CPU instruction that does that automatically for you, which I guess I don't think most CPUs would have one for this. But further than that, if the standard library doesn't implement the built-in in a way that's vectorizable, then it won't. And I think you'll see that in most cases, the standard library does not. However, okay, I'll get to it later, because in one particular case, there's something you can use as an alternative, which is what I had to use. But okay, anyways, so that's that one.
Is there any way to do comp time assertions to say like this must be vector, like this has to be a vectorized instruction?
For that, I don't think so.
I think it must be the built-in module. You can probably check, like in the same way that you can check like which OS and Concord, you can probably check this.
Well, you might have to know, like you might have to basically have a huge switch statement of like, this architecture supports it. Yes, true. This architecture doesn't support it. They have like a huge list. I don't know if there's like an automatic.
Insert or built-in.
Oh, okay.
Dot, like, so in the same way they do like if built-in dot OS tag equals Windows for like Windows C branch, you should be able to do like built-in dot CPU dot vector dot supports AVX 512.
But that would only tell you that it supports AVX 512. It wouldn't. So that would tell you.
So it would just error on platforms if you try to compile the platform.
It wouldn't cover the case where if the standard library implemented a user space version of that still vectorized it to some degree, it would not tell you.
Or more importantly, it won't know if AVX 12 support X. It won't know that
Right.
it only supports square root.
Well, you would have to know that, right? You would have to know AVX 12 does or doesn't support this operation. So it wouldn't, I don't think even that solution would go down to that granularity.
Oh, wait.
You would just have to know.
Okay, we can talk about it out.
Yeah. Okay, so let's do what was the other example? I think you can do, let's do, oops, caps lock. Nope. Well, I think that's one of them, right? Okay, what do we think? Is this gonna work or not work? Show of hands for yes, it's gonna work. And for it's not gonna work. Okay, let's see. I actually forget. It does work. Okay, it does work. What's
With
on
the
number?
9?
Sorry?
V round is with 9 in the assembly.
So that rounds every float up to an end. In all 8 of them. In
No,
parallel?
it's the IEEE 754 rounding mode.
Oh. Okay. There you go. I didn't even know that. Okay, that's super cool. What is another one? I'm trying to remember. Does anyone remember any more? There's square root. Okay, what about square root?
Let's keep going.
Yeah. I'm only gonna do this one and then one more.
Yeah.
Because the next one is actually the one that matters. Okay, so square root. Oops.
Yay!
Yes, it does. Okay, so what about sine? Oops. The one that I need. No. Bad. So I implemented vectors in my code at first and I thought, wow, this doesn't work. Or delete that commit. And then I eventually went back to it and like really tried to dig into why. And this is what I found. I'm like, oh, well, yeah, calling sinf at plt 8 times. That's not what I thought when the language reference said that sine supports vectors, right? So what you can use as an alternative, at least for sine specifically, I don't know if they implement any others, but the ZMath library from the Zig game dev project, they have a version of sine that does support vectorization. Because the implementation itself is vectorized. So it's like a user space version that's vectorized.
Is there like assembly that like they use or something?
I don't know. I don't think so. I think I looked at it for a second, but I didn't really like dig into it. You could look it up. Look up the ZMath library and you can. Are you looking it up right now?
Yeah.
Okay. Yeah. Get back to me on that. Okay, I'll try to speed this up. Okay. So the other thing. Wait, do you have it?
Oh, I don't understand this. I guess it looks like they're
using a
Like a tailor.
pari approximate in the fourth order.
crazy.
Okay. Okay, I'm gonna try to speed this up. So the other way to speed up your code is through multi-threading, which is much more difficult to get right, and will have a more drastic effect on like the actual structure of your code because you kind of have to actually like split it up and do things in other places and then synchronize threads, right? And all of this is very slow. So if you don't do it the right way, you're not actually going to get the benefits out of it. And in fact, you're going to make your code more complex, and it's just not going to be good. So how do we do this fast? Well, you don't necessarily just want to spawn a thread for each like conceptual task that you can like think of. You want to instead break the data up into larger chunks that can be computed independently. That's huge. The more you can do independently, the better, because then you're not synchronizing threads. The other thing is you don't actually want to be spawning threads, especially in a loop. Use like a thread pool, which Zig has a great one, standard.thread.pool. So you just spawn those once in the beginning of the program, and then you use and reuse them as needed, basically. So in order to avoid data dependencies, don't be afraid to duplicate work in your threads. It can be a lot faster to just recompute something than to like lock and wait for someone else to send you that information because you need it, you know? So in my synthesizer, for example, I kind of have like a save point basically at the beginning of every like 5 millisecond buffer. And then I break that up for each thread. Each thread has to duplicate the work of actually sort of hopping forward to the starting point of its section of the buffer. And that's okay. So it's not like I wait for a previous thread to finish the first section so I can start the second section. I just let them all go at the same time, and they have to do a little bit of extra work to make up for the data that they don't have. But it's like fine. It doesn't really make that much of a difference. Yeah, use a wait group. I don't know. And that's so basically, if you want to dig more into concurrency, watch Pradi's talk on proficient parallel programming. It was really good. I learned a lot from that. Okay, so my project goals, I'm really close to finishing like the core engine, and I want to make it just a little bit easier to kind of do state manipulations because that's what's going to allow me to add more effects basically to the synthesizer. I want to add a GUI, and the reason I gasped when you said DVUI is because I was looking at that and I'm like, wow, this is like perfect for what I want to do. I'm really looking at using DVUI for that. So hopefully that'll be one of the things I work on soon. I want to make cross-platform support better. So I'm doing my development on Linux mainly, and it's been amazing with Pipewire. And I'm able to set the preemption to full preemption, which basically makes the kernel more amenable to real time. So basically it will, it has like more points in the kernel code that it can context switch basically. So it will like, I'm probably not going to be able to explain it well in 2 seconds, so I'll just leave it at that.
Question over.
Yeah. Have you looked at using the real-time scheduling, or specifically the?
I'm waiting for my OS to get Linux 6.12, so I don't have to like look at it or get an out of tree thing. And then yes, I do want to do that. Oh, you mean the schedule? Right. So that's a different thing. So sorry.
Yeah.
So
I don't know if that's
so I do enable the real-time scheduling in my program when I spawn those threads. And then I think for Windows, if you use, I'm using port audio, and if you open the device in exclusive mode, I think it does that for you automatically, something like that. But I probably need to do a lot more debugging on Windows in that.
The deadline needs to run in milliseconds, or needs to complete every 1 millisecond, and have it so that the OS actually rejects new threads that they can't the deadline guarantee.
Yeah. So yeah, I need to look into that more. But I do have the real-time scheduling enabled in Linux at least, because that's what I mainly use. Another thing I'm looking at doing is implementing a plugin that so you can use this in like other digital audio workstations. That's probably going to be further down the line, but it's something I'm interested in looking at. particularly the clap plugin format looks interesting because it's like sort of an open format. And yes, my code is on my GitLab. I mean, you can either Google search it or I can put it in the Discord or something if anyone wants to see it. But yeah, any questions? Sorry for taking so much time. I didn't think it would take that long.
Yeah. So what is performance like? Like, are you staying well under the 5 millisecond
Yeah,
number?
yeah.
Sounded
So
like it.
so yeah, this is using 5 milliseconds right now, and it runs way worse on my laptop here than on my desktop at home. But yeah, so I can basically hit that 50,000 number on my desktop, which is a pretty cool. Now that doesn't mean I can hit that 50,000 number and do all a bunch of effects. As soon as you start to bring in effects, that can really drop it down a bit. But at the core of it, yes, I can hit that number.
So, like, what's your allocation strategy? Do you use Tiger Stack?
So, I do actually. So I'm surprised I didn't put that somewhere in the talk. Yeah. So what I do is I never allocate in my program. I do it all at the startup. You have to specify, you know, how many threads you want. So I spawn those up at start, and you have to specify the latency that you want, so it knows like, yeah. So it does all the memory allocation once at the beginning, and then everything is good to go. And it's easy to do that because the MIDI protocol is only 128 notes. So I only have to allocate enough space for 128 possible things or whatever, and you're good to go. So, yeah.
What about pitch bend?
Pitch bend?
Like,
Uh-oh,
how does
we
that
lost
fit
it.
into
We
the
lost it.
128 thing?
Sorry.
Like, how does bending a pitch fit into the schema of 100?
Sure. Oh yeah. So
Oh, I guess it's just
the
changing
pitch
that.
bend
Yeah.
Last
is
question.
I'm not modifying the MIDI index.
Yeah.
I'm reading the MIDI index once in the beginning, and then I'm doing all the modifications after
Yep.
the
That
fact.
makes sense.
So even if I hit the highest MIDI note, I can still go above that if I pitch bend it.
Yeah.
And yeah, I don't know why the program.
So yeah, we can probably get it running after.
Yeah. Oh, there it is.
Yeah.
Yeah.